Folks, welcome to the second video that we're doing today. This one goes over how to use Newton's laws using the second force formula. So after you've watched the video talking about the force problems, you should be ready for this, introducing the new material for today. And after we go through today's equation notes, you do have an assignment, the net force and acceleration worksheet. One other thing I do want to mention is that the 9 weeks is coming up at the end of this week. Therefore, these items that have been given to you do need to be turned in. At this point, I'm asking that if I'm not here, you do turn them into the substitute. Those would be the Newton's laws reading questions, the Newton's laws second law problems, Newton's second law problems, questions over force reading assignment number 2, and today's assignment, the net force and acceleration worksheet. Now, all of these can be found on Canvas. The first 3 do have videos. Of course, today also has a video that you're watching right now. So all of those can be accessed on Canvas in the Unit 2 force section on the main page. And then if you look at the top of the screen, you have day 1, day 2, day 3, day 4, day 5 notes. You can click on those and see what you need. If you have any questions, you can't find something, and someone in class cannot help you, email me. I will contact you back. Let's go ahead and get a start on this. So last time we talked about net force is mass times acceleration, but there's an actual, more straightforward, easy way to find net force, a second way to do it. So we want to make sure that you understand that when you talk about the net force on an object, that is the total force. If you have multiple forces pushing on an object, it will not accelerate due to just a single force, but the total of all forces pushing in one direction or pushing in opposite directions. So here's an example here. We have an object where the force 100 newtons is pushing in this direction. You also have an 80 newton force pushing that direction. When you combine these two forces together, that results in a larger total force. I think you can see, since they're both pushing in the same direction, what you would do is you would add those two forces. So the total force would be 180 newtons. And that would make the object accelerate more quickly than if it was pushed by either force by itself. Now, if we take the exact same two forces, but instead of pushing in the same direction, now the forces are fighting against each other. They are pushing in opposite directions. So you still have a 100 newton force pushing here to the right, but now to the left you have an 80 newton force. Well, I think most of you guys can see that the 80 newtons is going to partially cancel some of the 100 newton force pushing in the other direction. Now, one thing to keep in mind, since they do have directions, you do have positive and negative. So in math class, you learned on an XY axis that you've got positive going up and to the right, and you have negative going down and to the left. And we are keeping that same idea. So we would call this a positive 100 newtons, and this would be a negative 100 newtons. Now, to find the total, you still add them together, but you've got to keep in mind positive and negative, add those together, it's like subtraction. And so if you have a 100 newton force plus a negative 80 newton force, the total here would be 20 newtons. So this object will still accelerate. There is still a net force on the object, so it will still accelerate in the direction of the net force. However, because the force is partially canceled, that means that the acceleration will not be as great as if they had added together to make a large force. The smaller the total net force, the smaller the acceleration. The larger the total net force, the larger the acceleration. So that basically gives us this equation right here, that the total net force, you just add all the forces together. There may be only one, there may be 5. So this equation is basically saying as many forces as there are pushing on the object, add them. Force 1 plus force 2 plus force 3, and so on. Now in this case, we only had 2 forces, so you'd just be saying force 1 plus force 2. And one final note here for this first slide. The object's always going to accelerate in the direction of the net force. So in this case, the net force, if we were to draw that, you'd have a net force this way. It would be large, and you'd say that that net force is 180 newtons. So therefore, the acceleration would be in the direction of the net force. Now down here, we said that the net force is 20 newtons. It's still positive. So the acceleration would still be in that direction because the net force is still in that direction. The difference is, this is a smaller net force, so that means you're going to have a smaller acceleration. Now moving on, we added to this chart last time. We're going to go ahead and take a look at the back side of it. The back side of this chart for you is blank. But at this point, we've had enough different formulas that I feel that it's going to be worth our time to go ahead and just make a master formula list. Now, just like the front, this is not for my benefit. This is for yours. I want you to have a good reference. So on the front, this is everything that we know how to measure. These are the units you can measure it in. I will keep right up here on the desk some extra copies, so if for some reason you've lost your sheets, you've got extras available right here on the desk. So if you turn to the back, it will be blank. What I want you to do is add what we have here. So when you're making drawings, a good reference for like where should you put things, how should you label things, and then down here is going to be our formulas. Now, I've already got this filled out. You can pause the video at any time and go ahead and just copy this again on the back of your sheet. It is blank. Just go ahead and draw and write down these formulas. So starting out, we said normally when you have an object, you just go ahead and write the mass right there in the middle of the object. The accelerations and the velocities should go on either side, on the outside of the box. The forces you normally attach to the box, because if I have an object and I give that object a push, well, you're touching the object, and most people are okay with it. It makes more sense if it's actually touching the object. Now, but you got to be careful, because when those things add together to be the net force, you don't want the net force to be connected to the individual forces. These add up to be the net force. So typically, we can draw the net force separately on the outside. Now, if you do have an object that speeds up, and we said you have an initial velocity and a final velocity, what we asked you the very first chapter was, we'll go ahead and draw the object at its initial speed, draw the object at its final speed, just to remind yourself that you've got a starting speed, and at any speed it was in different spots when that happened. Now, if you scroll down here, again, at any time, you can pause the video to write down what you need to. These are all the different formulas we've had. You've got your basic speed formula. If you have a constant or an average speed, cover that up. That's distance over time. Distance, those are next to each other, so distance equals speed multiplied by time. If you have a graph, a position graph, we said that this velocity is the slope of the position graph. So that would be y2 minus y1 over x2 minus x1. The displacement is just how much your position changed, which is the y-axis on your graph, y2 minus y1. After that, we moved on to acceleration. That's a basic acceleration formula, and here it is rearranged for time, final velocity, and initial velocity. We had done metric conversions, and so for the metric conversions, you've got kilo, hecto, deca, your base units, deci, centi, milli, and then finally, this chapter for our force formulas, you've got your net force triangle with force, mass, and acceleration, and then today's new formula, the net force is all the forces being added together. So make sure that you have that done before you move on. And once you're ready, you can move on to the second part. So when we talk about forces being added together, depending on the direction, we said they're going to add or they're going to cancel. And so in a situation here where we've got a tug of war, you've got a force of the people pulling this way, you have the combined force of the people pulling this way. So they are both pulling on the rope. If this pull is bigger, then everybody's going to start accelerating this way. You notice that when people start falling down towards the direction of the stronger force. So in that case, the net force would be towards this end, the people pulling in that direction. Now, if the forces are being added together, all in the same direction, so here we've got lots of different people combining together to push the car. No one person was strong enough to really get that car moving. So we've got 1, 2, 3, 4, 5, 6 people pushing this car. So all their individual forces add up to one large net force when they're all pointing in the same direction. Now, you might remember this from our very first day of the chapter. We talked about Newton's first law. An object in motion tends to stay in motion at a constant speed and in a straight line. And if it's not moving, then it also keeps that constant speed. In that case, the speed is 0. It's at rest, and it's going to stay at rest. Now, we said the only time that that's going to change is if it's acted upon by an unbalanced force. So if the forces are not balanced, if it's pushed harder in one direction than it is another, then you have a total force. After everything else may cancel out, you still have a leftover total force that's going to cause that object to accelerate in the direction of that unbalanced force. And that directly leads us, the reason I brought it up again is because we're going to talk very quickly about balanced and unbalanced forces. When you have balanced forces, well, all the forces, if there are any forces acting on it, they all add up to be zero. Any positive forces are canceled out by negative forces. So when things are balanced, when forces are balanced, the following are true. The net force is zero. All the forces, all the positive negatives add up to be zero, so it acts as if there's no force at all on it. Now, if the net force is zero, then there's nothing to cause it to accelerate. Every forward push is balanced out by a backwards push, so it doesn't speed up, it doesn't slow down, the object doesn't change speed. That does not mean it's stopped. It simply means that its speed will not change. If it was stopped, it will stay stopped. But if it was moving at some speed, let's say 20 miles an hour, then it will continue to move at 20 miles an hour because there's no leftover force to speed it up or slow it down. They've all canceled out. And not only at constant speed, but remember, it'll also move in a straight line. There's no leftover forces pushing it sideways to make it turn if all the forces have canceled out. So an object that has balanced forces acting on it, we do say that in that situation the object is in equilibrium. When you have balanced forces, we call that situation equilibrium. There's two situations where you can have balanced forces. The first one is, well, there's absolutely no forces acting on the object. So if you think about an object in space, if you were sitting outside the space station and you have an object and you just let it go, it's not going to go fly off in any direction. There's no forces to make it speed up or fly off. So it's just going to stay there and it's going to hover and it's going to float. So that situation is extremely easy. Here, you've got a net force of zero because there's no forces acting on it. Now the other way to have net forces balanced, to have a net force of zero, is that you do have forces acting on the object, but they're equal and opposite on both sides, and so they cancel out. So the simplest situation that I can think of is if you just have two equal forces. So that could be, let's say, 20 newtons pushing this way, and you've got another 20 newtons pushing that way. Now, which one of these would be negative, by the way? We said this direction is positive, this direction is negative. So if you look at the arrows, I can put the arrows on either side that I want, but it's the direction. This one should be considered a negative. And so you add those two together, 20 plus a negative 20, equal forces pushing in opposite directions. They add up to be zero. So again, in this situation, the net force will equal zero. And when the net force is zero, we did say that the acceleration is zero, so the speed will stay constant. So anytime you have a net force of zero, understand that this object will not change its speed, but that does not mean that it's not moving. It's just not speeding up, slowing down, or turning. Now, what if we have unbalanced forces? They occur when an object has multiple forces acting on the object and they do not cancel out. So in this case, the net force would not be zero because the forces did not cancel. You have a leftover force pushing it forward, backwards, up, down, and the object's going to accelerate in that direction. The acceleration will not be zero. It'll accelerate in the direction of the net force. So you could have the object speed up, you could have the object slow down, but if the object's moving this way and the net force is pushing sideways, that doesn't push it forward or backwards to speed it up or slow it down. That pushes it to the side, which just simply makes it turn. So two simple ways to have an unbalanced force. The first way is that you could have an object that only has a single force acting on it. So in this example, if you have a single force pushing this way, so let's just say that that force, I'm going to make up a number. Let's say that's 50 newtons. Well then, in that case, the net force is going to be 50 newtons. The only force acting on it acts as the net force. And then you have multiple forces, which you've already kind of seen some examples of. And so here, if I come up with another few numbers, let's say that you've got a 50 Newton force acting this way, and you've got a 40 Newton force acting that way. You could call this force 1 if you'd like. You can call that force 2, although whichever one you say is 1 and 2 doesn't really matter. When those happen, the 40 newtons partially cancels the 50, but not totally. And I think you would see that since the 50 is a backwards direction, that would be a negative number. If you add these together, the net force in this case would be 40 plus a negative 50. That's a negative 10 newtons, which tells us the net force is going to be in the negative direction that way. But of course, you can see that by saying the bigger force is pushing in this direction. You get the same idea. So let's go ahead and try some problems. The sheet that you're going to be working with has a lot of problems like this. Now I'm hoping that they come out to be pretty simple for you. And I'm just going to make sure that there's nothing I am missing out. Actually, that does remind me, when you do have unbalanced forces, we said that the object accelerates in the direction of the net force. So if the net force is pushing this way, even if you don't know what the acceleration number is going to be, you know it's going to accelerate in the same direction as the net force. Over here you have two forces pushing, but the total net force was pushing backwards, so whatever the acceleration number may be, you know that the acceleration is in the same direction as the net force. So going to these problems, we've got 20 newtons and 30 newtons pushing this way, and we also have a 10 newton force pushing that way. Now, you notice that I drew the forces on different sides of the boxes, but they're all pointing in the same direction. Therefore, none of them are going to cancel out. It's just this person pushed, the second person pushed, and the third person pushed all in the same direction. The forces are going to add together to be a large force. So if we're going to solve for this net force, what you know is the first force, the second force, and the third force. All you know is forces. You can't use force equals mass times acceleration. You're just going to be adding together these forces. Just take a look, every problem, and think about what you know. And based on what you know, if you have multiple ways to solve for it, that's going to help you figure out the right equation to use. So for this one, you know that the net force is force 1 plus force 2 plus force 3. And then if you add those together, none of these are in the opposite direction. They're all positive. So that would be 20 newtons plus 30 newtons plus 10 newtons. And when you add those all together, you should be able to do that one in your head. 20 and 30 is 50 plus another 10. That is a total net force of 60 newtons. So if I were to ask you to draw that net force, you would draw a nice large arrow going that way and say the total net force in this case is 60 newtons. Now in the second example, we have the exact same three forces. The only difference is, and I went ahead, let's separate these. I went ahead and put this one in a slightly different color just to make it stand out. You still have 20, 30, and 10, but this time the 30 newtons is going backwards. Now I'm not going to put the negatives on the sheets for you. When we show you these examples, I do expect you to take a look at the direction and say, are these positive or negative? So for this one, since that one's going backwards, this is now negative 30 newtons. And so we can use the exact same formula, but this time it's going to be slightly different because of the force going in the other direction. And you've got 20 newtons, but instead of a positive 30, you are now adding a negative 30. So that's kind of partially canceling things out, but you still have this 10 newton force going forward. So if we add up the positives, 20 and 10, that's 30 newtons going forward, but then you got negative 30 newtons, that's 30 newtons going backwards. So what happens? Those forces totally cancel each other out, and in this situation, the net force ends up being 0 newtons. And so if I were to ask you if the object accelerates, well, yes it does. In this case, the net force is in that direction, so whatever the mass is, that'll help determine your acceleration, but you know it accelerates in the direction of the net force. In this case, the net force is 0, so does the object accelerate? If it feels like it's not being pushed, because all the forces cancel out, in that case, the acceleration is 0 because the net force is 0. So the net force and the acceleration are always linked. The bigger the force, the bigger the acceleration. If there is no net force, there is no acceleration. Now again, that doesn't mean the object's not moving, it just means that it's not changing its speed. It could be stopped, but it could be moving at a constant speed. Now if I were to ask you, are these balanced or unbalanced, what would you say? Well, for this one, you would say there is a net force, it's not zero, so your answer there would be that your forces are unbalanced. But in this one, your forces totally cancel out, so in this case, we would say that your forces are balanced. I'm just abbreviating here, so we don't have to write out the whole word, but there will come times where not only do I ask you to solve for the forces and the accelerations, but I will ask you, are things balanced or unbalanced? Unbalanced forces accelerate, balanced forces means the net force is zero, and there is no acceleration. And then, as we work towards our last few problems here, again, we take a look at this and we say we can solve for the net force, but you notice I've added an extra piece of information. And so this is going to be a two-part problem. So we solve for the net force. Before we do that, we should label what we know. And again, I don't care which one you call force 1, 2, or 3. It's whatever makes you happy. So I'm going to say force 1, force 2, and force 3. But then we have this. And sometimes in the past, I've had students accidentally call this a force, but these are not measured in newtons. This is kilograms. Now, if you look back to your sheet, kilograms measures mass. Now, if you didn't remember that, okay, but make sure that you're trying to commit those things to memory. You should be using them over and over again, and they should start to sink in. So coming back here, since this is measured in kilograms, then you should be able to label that that is the mass. So we have these three forces, and we have the mass. If I wanted to find the net force, I can't use force equals mass times acceleration because I don't know the acceleration, but I do know the individual forces that are pushing on the object, so I can go ahead and add those up. There's one last thing you should be thinking about though. These are pushing in opposite directions. Now if you remember in math class, up is positive, down is negative. So before you actually add your numbers in, always take a look at your arrows and say, if they're in opposite directions, which side am I going to call negative? And make sure that you put negatives on there so you don't forget, you don't do all this work and it comes out wrong because you started off by simply forgetting about the negative direction. So if I want to find the net force, we're going to, again, use that formula. The net force is force 1 plus force 2 plus force 3. And if I add these together, that would be a positive 500 newtons plus a negative 200 newtons plus a negative 100 newtons. And if you add all of those together, that's 500 plus a negative 300. So the total answer would be 200 newtons. And you see that that's positive. So that means that the net force, the total force, after everything else is canceled out, is going to be in the positive direction. So off to the side, we can draw the net force. The total of all of those is going to be 200 newtons. Now the second part of the problem says, what's the acceleration? Now, you don't have initial and final velocities, you can't use that formula, but we have found the net force and we do know the mass. So we can use your formula triangle. And I'll put that up here once, just to remind you. The formula triangle for that one, net force on top, mass and acceleration. So if I'm looking to find the acceleration, you cover that up, and that is net force divided by mass, since they're sitting on top of each other. So you can go ahead and plug those in. The acceleration equals the net force divided by the mass. So that is total force, 200 newtons, divided by your mass of 25 kilograms. And so if you punch that into your calculator, see 100 divided by 25 is 4, so this must be 8. And just a friendly reminder, when you have a newton divided by something, you can break the newton down into kilograms times meters per second. And when you do that, you should see that the kilograms cancel the kilograms, and what you have left is meters per second. So that object speed is changing 8 meters per second for every second that that force is applied. The next problem, again, we'll separate these so it's a little bit easier to see. Solve for the net force and solve for the mass. So let's label what we know. In this case, we've got a first force, we have a second force, and then here, even if I don't label it acceleration, I believe on your worksheet I don't label it A, but you do see the units, meters per second per second. You should see that as acceleration, and it's going this way. So again, before you start doing the math, think to yourself which objects have positive and which objects have a negative direction. So in this case, this is pushing forward, that's positive. This is pushing backwards, that's negative. So let's throw a negative in front of there to remind us. This one is pushing backwards, so that is also a negative value. And I think we're ready to go ahead and start the problem. In this case, to find the net force, we can still add those two forces together. So that's going to be force 1 plus force 2. I'm not going to write the formula again. I think you've seen that enough. So that's 15 newtons plus a negative 27 newtons. And when you add those together, what you get is negative 12 newtons. So there's your total net force. The object is going to accelerate as if it was only being pushed by 12 newtons in this direction. We can go ahead and label that. The total net force is negative 12 newtons. It's a good habit to get into, labeling it once you found it, because oftentimes I may have a problem that's got 2 or 3 parts, and you might have to use that answer to find the next one, and adding it to your drawing makes things a little bit simpler. So now it's time to solve for the mass. We've got your net force, we have your acceleration, so looking at the mass, it would be force divided by acceleration. So we plug those things in. M equals F net over A. And so that's negative 12 newtons. And you also have a negative 4 meters per second per second. Now those newtons, remember, are going to cancel. Kilograms times meters per second per second. And so you should see the meters per second cancel. All you're left with is kilograms. And I'll point out, you've got a negative here and a negative there, and you guys know that 2 negatives are going to cancel each other out when you multiply or divide. And so we've got 3, positive 3, and our units that are left over are kilograms. So there's the mass of the object. Now these are pretty basic, the problems that I have you doing today. They all go along pretty well with this, with the exception of your last problem, which is a bit of a challenge. It's a bonus problem. Which reminds me, we do have one more example to go through, and it's right here. So pay careful attention. This is different than the ones we did. You're still using some of the same formulas, but in a different way. So in this case, we happen to know the net force. That could be a situation where you were measuring it, or you knew the mass and the acceleration, you were able to calculate the net force. And we happen to know that there's a downward force of 200 newtons acting on the object. What we don't know yet is how hard is it being pushed up so that the total force adds up to be 900. Now, this sometimes does cause problems for people. We want to make sure that this is as clear and easy as possible. And I want to remind you, take a look at your arrows. Is there arrows in opposite directions? If there is, you've got to make one of those directions negative. So we have up and we have down. We're going to go ahead and make the down negative. And this problem actually isn't that bad as long as you've seen what to do. And so we've got a net force. We have force 1 and force 2. We can write the same basic equation. Net force equals force 1 plus force 2. There is no force 3 in this equation, so we're not going to go ahead and put a force 3 in. And at this point, I think the easiest way to solve it is to plug in your numbers and then just move it around, like in math class when you solve for x, just to see what force 2 would equal when everything else gets moved to the other side. So if we plug in our numbers, the total force, everything adds up to be 900. Force 1 is negative 200 newtons. And we don't know force 2, so you don't put a number in for it, you just leave it as force 2, just like in algebra when you label something that you don't know, x. So if I want force 2 by itself, I need to move this to the other side. Now you remember from math class that if your adding or subtracting, you do the opposite to it. So how do I cancel out this negative 200? Well, if I want to cancel out a negative 200, I need to add 200. And when you do that, those cancel. But if you do it on one side, you have to do it on the other. So if I added 200 here, I need to add 200 newtons on this other side. And when you come up with that, all you have left over here is force 2. And what